So, let us now apply the concept that we have learned to a simple example, a very simple network of pipes. So, we are talking about two tanks. So, let us say this tank, the elevation of the water is z equal to 40 meter, and it is fed through a pipe. So, this would be a rounded edge and it goes into a valve. So, this valve is a half open gate valve, and then it again goes through a pipe and an elbow. So, this one is a 90-degree elbow. Then I have a long pipe which is of length 200 meter, and this is a GI pipe with a diameter of 5 centimeter, and my roughness is 0.003. Okay. And to feed this tank, it again goes through an elbow. So, this is a 90-degree elbow, and then it goes through another valve, this time it is an open gate valve or a globe valve, and then it feeds the tank. Okay. And this is again a rounded edge, and in this tank the height of the water surface is z equal to 5 meter. So, let me call this as 2 and let me call this as 1. So, water flows from reservoir 1 to 2. So, there is no pump, we are just using gravity to fill up the reservoir 2 from 1, and you are supposed to find the flow rate. Okay. All right. So, we will start by writing the energy balance. So, let us write the energy equation between 1 and 2. Okay. So, I am going to assume that there is a control volume, okay, which I am not drawing it here, but you know how to choose a control volume. So, the control surface on the upper surface is kind of normal to the free surface. So, it is the free surface itself. So, the velocity is normal to this surface, and likewise for 2. So, I will assume that this is a one dimensional at the inlet and at the exit, and of course, I am not so much worried about what happens inside as far as the inlet and outlet are concerned. Okay, so if I apply the energy equation, then I would see V square over 2g plus P over rho g plus z. This is at station 2 should be equal to the inlet, which is V square by 2g plus P over rho g plus z at 1, and then minus HL, which is the head loss term, and minus HS, which is actually the head because of shaft work. So, this is the shaft head, which actually, if you remember, was given as Ws by G. Of course, in our case this is 0 because there is no shaft work. We will now make some assumptions that the flow at surfaces 1 and 2 are kind of very small, okay, because so we will assume that the cross section area of reservoirs is very large compared to the dia of pipes. Okay. So, the speed therefore, V1 is nearly equal to V2, which is nearly 0. Okay. Further, we are going to assume that this is at least in an instantaneous or a small time instant, we can neglect the unsteadiness. Of course, that is not entirely true, because as you know, this free surface is going to recede and the one in tank 2 is going to rise. But we will still say that that rate is so small that at least in a quasi steady assumption, we should be able to apply this equation. Okay. The flow is of course incompressible, and the free surfaces, so P1 is actually same as P2, and there is atmospheric pressure. So, atmospheric pressure on the free surface 1, atmospheric pressure on free surface 2. If I do that, then this term goes away, okay. This term cancels out on both 1 and 2, and so I simply get Z at 2, which is 5 meter. So, I have therefore 5 meters. So, this energy equation would imply that 5 meter is equal to, this term goes away, this cancels out with this, Z at 1, which is 40 meter, and I have a head loss which is HL. And therefore, this implies that my head loss is 35 meter. Okay. Now, I ask myself, who contributes to this head loss? So, obviously, if I look at this diagram, I have a pipe. So, let me list the things here. So, I have a pipe which is about 200 meter long, and then I have the fittings. Okay, so I have an entrance, okay, but with a rounded edge. So that's 1. So maybe I number them. So this is 1. Then I have a gate valve, which is 2. Then I have an elbow, which is, I am numbering number 3. Then I have another elbow, which is 4. Then I have a globe valve, which is 5. And then of course again an expansion, which I am calling 6. So I have 6 fittings. So these quantities, they actually contribute to my head loss. I must account for all of them. Okay. So I am going to write this as that HL is because of the pipe and the fittings. So I will just summarize it in this manner, that I going from 1 to 6, this is the loss factor Ki times Vi square by 2G, plus the loss because of the pipe, So this is the Darcy's friction factor inside the pipe times L by D plus V square average by 2G. Okay. Now the next task is to estimate these Ki's and F. And once I do that, I know HL, and then I could probably get the value of the speed. So let me make a small table here about I and the Ki, the different fittings. So this is, I have 6 of them. So the first one is a contraction. It's a well-rounded contraction, and therefore the Ki is kind of small. So we have seen a little while ago that for a rounded contraction from an infinite area to a small pipe could be as low as 0.05. The next is the half open gate valve. And for this, the number is 5. The next one is an elbow, and this is a 90-degree elbow. And for this, the K is 0.9. The fourth one is also a 90-degree elbow, which is again 0.9. The fifth now is a gate valve, a globe valve. So this is a fully open globe valve. And a globe valve has huge losses. So this one would be 10. Okay? And then of course you have the exit, which is 1. So if I look at summation Ki, I going from 1 to 6, I need to add them up, and that is 17.85. So I could therefore write that my head loss, which is 35 meter, is actually equal to 17.85. Now I'll argue that the speed throughout the pipe and throughout the fittings is identical. So it's exactly the same diameter, which is 5 centimeter. Okay. In fact, we have already said that when we go through expansion or a contraction, it is the narrow region which actually matters. So it is V square by 2G. And for the pipe, I am simply going to write this as F times L. So the length of the pipe is 200 meters, and the D is 0.05 meters, it is 5 centimeters, and this divided by V square over 2G. If I can estimate F for the pipe, then I should be able to get what is V square, and therefore V. So now I'll have to use the Moody chart. So this is an iterative process. So what I'll do is I'll assume that flow in pipe is fully turbulent. Now let me recall the Moody chart for you. This is how we had shown it in the last class. So this is the friction factor, and this is the Reynolds number through the pipe. Of course, we had the laminar regime where this was given as 64 by RED. And then somewhere here the flow transitions to a turbulent state, and then at a large RE it becomes fully turbulent. So if I sketch here for the curve for 0.003, it will probably look something like this. So, this would be the curve for epsilon by d equal to 0.003. And there would be other curves for different roughnesses. In fact, a higher epsilon, a higher roughness would have a larger f value and it would lie above it, and lower epsilon by d would lie on the lower side. Now, this is where the flow has become completely turbulent, and therefore, the f value does not seem to depend on Reynolds number. So, that is what I am assuming, that let us say the flow is lying in this regime and I can choose this value of f from the Moody's chart. This value I have read out, it is roughly 0.027. Okay. So, if I lie in this regime, then the Reynolds number does not make a difference and I can use this value of f, and this is something like 1 into 10 to the 5th. Okay, so, I will assume 0.027. Mind you, if I had different values of epsilon, then the value would be different. Okay, so, I have used this. So, this is the Moody's chart. So, I plug that in here and I would get v square by 2g to be 35 divided by this whole thing, which is 17.85 plus 0.027 times 200 divided by 0.05. And if I work this out by using g as 9.81, then this turns out to be 2.336 meter per second. Okay, that is the speed of the water through the entire pipe. What I can do now is check if my Reynolds number actually works out in the regime where I can assume that there is no dependence on the Reynolds number. So, I use this now to calculate RED, which is rho v d by mu. So, if I plug this value of v, I would get this as 1.2 into 10 to the 5th. And indeed, this is larger than the Reynolds number that we had assumed. Therefore, our assumption holds. Suppose it did not. Okay, suppose I found that this Reynolds number lies somewhere here, this value. Then what it implies is that the value of f that I assumed was too little, and I should actually choose this as the value. So, I use this Reynolds number which I have found out, estimated, and then estimate this value of friction factor. Again go back to this formula, plug the value of f and recalculate my speed, and from that speed again estimate my Reynolds number and see indeed if I have converged. So, I could iterate and get the final value of v. So, here we were fortunate that right in the first instant we were able to get the answer. How about the q dot? The q dot is pi d square by 4 times the v, and this turns out to be 4.6 into 10 to the minus 3 meter cube per second. So, that is the flow rate through the pipe. Okay. Now, it would be very nice to compare this with the ideal situation. Suppose there are no losses. Okay, so we want to now look at the situation where suppose there are no losses. Then what would be the speed of the flow in the pipe? I would like to then apply these equations carefully somewhere else. So, let me number these as, let us say, the station A, this as station B, and of course, this is 2. So, let me now apply the energy equation between 1 and B. So, this point, the free surface, and B is the entry to the reservoir. I could use some other points as well, but let me just try this out. So, this would be then B, and this would be 1, and there are no head losses because I am looking at an ideal situation. So, let me estimate now the various quantities. I will use the same assumption that I have a very large reservoir. So, V1 is 0. Okay. Further, P1 would be P atmosphere. Let me assume that this height is H1. Okay. So, I can now estimate what is the pressure at location B, and of course, I can also estimate what is the Z at location B. So, Z at location B would be simply 5 meter minus H1, right, and Pb, the pressure here, I will assume that it would be the same, of course, an assumption because there is a flow here, but I will assume that the pressure is primarily hydrostatic, and that is simply P2 minus this. So, it is P atmosphere plus the hydrostatic head, which is rho g times H1. So, now I plug in the values. So, at the station B, so I have V square by 2g. The pressure I am going to call it as P atmosphere by rho g plus, of course, I have H1 here, and as far as the Z is concerned, at location B, the Z is simply given over here, which is 5 minus H1. So, this is now equal to the quantities on station 1, which is over here. So, the velocity is 0, the pressure is atmospheric pressure by rho g, and my Z is 40 meter. And you will see this cancels out, the P atmosphere term cancels out, and I am going to get V square by 2g is actually 40 minus 5, which is 35. Okay. And if you evaluate this, then V would turn out to something like 26.21 meter per second. Okay. So, if I had no losses, the rate of filling of the reservoir at lower height would be much larger. So, Q would be much larger. Okay. Q is actually the velocity times the cross sectional area. But if you had losses, then I have only 2.3 meter per second. So, it is about a 10-fold reduction in speed. So, I hope this problem illustrates to you how to take care of fittings. We will now stop here. and we will move on to the next topic in the next session. Thank you.